Hello everyone, welcome to the third lecture of week 12. This lecture is also about model interpretability. So in the previous lecture we talked about multilingual aspects in interpretability, and we ended discussing about the role of attention mechanism as well as feed-forward networks. So this lecture will focus on what are feed-forward networks, how do we interpret what is going on inside them. So certain attempts we'll discuss. So we'll talk about feed-forward networks as key-value memories. That's how the lecture will start. And then we will discuss an interesting concept called causal tracing. Now, when it comes to the transformer architecture, there are two main components, right, about which we can talk about interpretability. So, of course, we talked about the layer outputs, right, the outputs from different layers. So, you can do logic lens to project them. But inside a layer, you have self-attention, you have multi-layer perceptron, the feed-forward network. So, for self-attention, if you remember, we talked about using induction hypothesis on how the in-context learning works. So, this is a slide that is copied from one of the earlier lectures, where we discussed how the induction heads in the self-attention layer, they help in prefix matching and copying mechanism, right. But what can we say about the feed-forward network? So, we will take this particular paper and discuss, so which talks about how we can view the transformer feed-forward layers as key-value memories, right. So, this was from 2021 EMNLP. Now, this is a picture that gives you the crux of the idea, the hypothesis that the paper put forward. We will come back to this picture again, right, after I discuss this idea a bit more. But yeah, just to give in brief summary of what this paper discusses. So, let us say you are feeding this particular input in your decoder, stay with you for A, and you have to now decode the next word after A. So, it will go through transformer layers. So, let us say in a particular layer, it will first do self-attention. Now, this paper does not focus on self-attention, so you will have the output. So, this is the self-attention output for the word x5, the fifth word A, right. And now you will have the feed-forward layer. Now, what it says is that, so this vector, that is the self-attention output, will get multiplied to keys. So, it says this feed-forward network, that is, I have the self-attention output, then I have an up projection and a down projection. So, let us say this self-attention output is same as the model dimensionality. So, let us say this is your D dimensions, and this they call as DM dimensions. This we know as roughly 4D, and this is again D dimensions. So, what they conceptualize is that there are DM many memory cells, and you have this matrix that is D cross DM, another D cross DM. There are two matrices. And this they call as the keys. So, this they visualize the keys. So, you have DM many different keys. So, each key is of dimension D. So, each key D dimension, and similarly there are DM many values. So, you have keys in the up projection and values in the down projection, and again each value is of D dimension. Okay. Now, what the keys and values individually do? So, the keys, they try to see what is the pattern in the data to which I can associate this particular prefix at this point. So, stay with you for a while, for A, you have to predict the next word, possibly while. So, now you will see in the training data what are the similar patterns. So, that is what keys are storing. So, individual keys are storing individual patterns. So, like if you look here, maybe the key 2, it is storing patterns like it will take A every point in A, every once in A, and for A, it is storing certain patterns. And now, whichever pattern gets the highest similarity with this particular self-attention output at this point, corresponding value will be triggered, and this value stores the output token distribution, like which token will come after this prefix. So you have a nice key values where key stores after this pattern. Typically you follow this distribution of tokens, right? So keys are storing the patterns and value is storing what is the next token distribution. And so this is what they hypothesize happens in the key value networks, right? And because this particular value will be triggered the most, you will get the corresponding token distribution, and this will help you getting the final output word. Now we will look into details of this proposal, and then we'll come back to this picture again. Okay. So what this paper proposes, you can visualize this MLP, multi-layer perceptron, as key value memories. So what is the idea? Let's say we have a d-dimension vector, right? That's the input. You can think of it as the self-attention output, right? So this is a vector corresponding to some input test prefix. So this is d-dimension, and this is the output of your self-attention mechanism. Now how you can express your feed-forward layer? So this is, right, I mean, I can call this something like, if this is 1 cross d, K transpose is d cross dm, and V is dm cross d. So finally you get 1 cross d again, right? So together x times K transpose, so K is dm cross d, so K is dm cross d, and V is also dm cross d, right? So K transpose multiplied to x, you get the hidden layer after putting the activation. So this gives you the hidden layer of the feed forward after putting the rally or another activation to the input. So this is after putting value, this is what you get here, and then you multiply the values, right, with that, and you get the final output. So both K and V are parameters that you are learning, and F is a nonlinearity like value. So this is how you visualize this particular equation, right? That's we are quite used to that. I mean, this does not feature, for example, bias terms, but this is what is a feed forward layer. Now they compare this to the neural memory idea. What is the neural memory idea? So this is very similar to attention mechanism. That is, you have let's say you have dm many key value pairs, right? And each key value is again d-dimension. So you can say each key is d-dimension, and each value is also d-dimension. Now how do you put attention over these key values? By your vector x. So through your vector x, how do you put attention over these key values, right? So what you do, so let's say you have this d-dimension vector. So first you have this dm many keys. So you have k1, k2 to k dm. So what you do, you take a dot product of x with each of these ki's, right? X dot ki's. Now once you get the dot product, what is the next thing you do? You take softmax. So this is as if you are taking exponent of each value dividing by the normalization constant, right? This is what you do. Now what is your final output? So this will be the weights through which you will multiply with the values. So this is what you can call it, probability of ki given x, and then you multiply with this probability the value I, and you sum it over all the dm memories, right? So another way you can write it as, I will do x times k transpose, right? Then do a softmax, right? This gives me the probability, then multiply with the value. This is another way of writing it. Now once we are convinced that this is the way we write neural memory, and this is the way we write the key value the feed forward network, you can easily see similarity between FFX and MNX, right? So instead of a nonlinearity, I am doing a softmax here, but otherwise they are similar operations. So this is a background by which they say, okay, so then we can see the feed forward network as key value memories, right? So that's the idea. So now if I look at this such key value memory, so you have the dm as the hidden dimension, and this is the number of memories that you have in that layer. So each layer will have different memories, so, right? Each layer has its separate feed forward network. So each layer has separate memories, dm memories, and this activation that I have, which is the hidden layer, it is a vector of unnormalized non-negative coefficient for each memory, right? So we know which memory is getting triggered more than others, right? So this is your memory after applying this f x dot k transpose, the projection and the nonlinearity. and each mi is the memory coefficient of the ith memory cell. So, that is how they visualize this feed forward network. Now, given this connection between neural memory and feed forward network, so they put forward a conjecture. So, what is the conjecture? So, this is that every key vector k I, right. So, now just to visualize what is k I. So, you have this x. Now, what you can do, so you can say okay, so this is take ith memory cell here. So, I have this connection of this is d cross 1 weights that connect the input to the ith memory cell, right, and this is exactly what is my k I, ith key. So, I am multiplying this whole input with this k I get this one particular memory cell, right. And similarly, if you put another memory cell j, you will have another d values d cross 1, that is k j, right. So, for every memory cell to go from input to that memory cell, you need a particular key, d dimension key, right. Now, the conjecture says what do these keys store? Remember, these keys do not depend on the input that you are feeding. They are the parameters that you would have pre-trained already in, right, from your pre-training. So, what do these already store? That so that you can do a certain transformation from the input to going to the memory cell. So, they say they capture a particular pattern or a set of patterns in the input sequence. Okay. So, each key will store a particular pattern, and for each key its corresponding value, right, that will help me project from here to again this d dimension, the value, right, the output. What does that store? It says okay, so that stores what is the distribution of tokens that follow this pattern. So, key stores the pattern and the corresponding value will store what is the token distribution, but there will be separate token distribution which each of this memory cell. So, this j will again project to this and so on, right. So, key value association, key store the pattern, a specific pattern, and value stores a particular token distribution. Okay, now we can come back to this picture, and now you can understand this much better. So, when we are feeding an input, I want to know what is the next word, right. That is the task of an autoregressive model. So, what it does, so once you have the self attention output, it first finds out which of the keys, which of the DM keys stores a pattern similar to what I am seeing right now, because once I find a similar pattern, then I can use its corresponding value to figure out what will be the token that will follow this pattern, right. So, it first compares with each key and says okay, k2 is the highest match, it can be a simple dot product, I mean you just multiply this k2. So, this is the highest match given by this 1.5, this is very low 0.2, 0. So, I will now see, I will look at the token distribution that V2 is providing me to help me decide what is the next token I will predict. I will look at the token distribution that V2 provides, right, and I use that to predict my final token in the decoding, right. So, that is the conjecture. Now, what kind of experiments did they do to support this conjecture, right. So, first of all, they say that so key vectors in the feed forward layers, they act as pattern detectors over this input sequence, right. So, let us say I have an input prefix, I am up to x1 up to xj in the input, I want to now predict xj plus 1. So, what I will do at this point, I will have some self attention output for xj. Now, each key anyways independent of the input stores certain particular pattern, right. So, this is independent of the input, it stores certain patterns. Now, what you do, so they say okay, can we analyze the keys of a trained language models feed forward network. So, they say okay, what we can do, we can find out from a training data which training examples, I mean mainly the prefixes, are most associated with a given key, right. So, where the input text, where the memory coefficient is the highest. So, they say okay, how do I find out what is the pattern that each key stores. So, let us look at the training data and we will try out which prefixes have the highest similarity with a particular key, right. So, and see how many keys are there. There are L layers, and each layer there are DM keys in each layer. So, there are quite a few number of keys, right. Each layer has separate DM keys. So, for each key they will find out what are the examples in the training data that have the highest similarity. So, how do they do that? So, let us say I have a key KIL and that corresponds to the ith hidden dimension of the lth feed forward layer. Now, what you do? So, let us say I am passing a prefix x1 to xj, right. Now, I am talking about lth layer. So, let it pass through in residual stream. So, I am going to the lth layer. I even have the self attention output. So, xjl is actually the self attention output, right. Now, I compare its similarity with the key in that ith layer, right, the ith key. So, this is xjl is a vector, d dimension vector, and KIL for the lth layer, the Ki key is again a d dimension vector. I take the similarity and do ReLU. So, I will get a value. I mean, if it is greater than 0, I will get something, otherwise I will get a 0. So, I will compute it for every prefix from my data, right. So, I will do it for x1, x2, I will do it just for x1, x1, x2, x1, x2, x3 and so on. I will keep on doing that and find out which prefix has the highest similarity. I mean, I will just compute these values. So, give this example, like suppose I have this sentence I love dogs. So, I will do it for I, the representation for I love dogs, right. And if we do that, we will retrieve what are the top T trigger examples. So, top T prefixes whose representation at layer L, they yield the highest inner product with KIL, right. So, you find some top T trigger examples that are matching, right. So, I guess you get the idea. You keep on trying with all the data in your training with all the prefixes and see which of these have the highest similarity. So, you keep on storing this ReLU value per prefix with a particular key, and then for each key you find out the top T prefixes that have the highest similarity. Now, they do pattern analysis, like do they really mean anything? I mean, whatever prefixes we found, do they really capture certain pattern? So, what they do, they take some NLP graduate students and they say, okay, for each key I will have 25 prefixes that I have retrieved, and you try to identify what is a repetitive pattern that occur in at least 3 prefixes, right, and which can possibly indicate some connection to the key, right. I mean, otherwise, I mean, if this was thrown at random, I would never find such a connection. So, I did in these top 25 prefixes, do I find some specific pattern, because that will be a very nice evidence that yes, this key is storing some specific training data, right. And you describe each recognized pattern, and then you classify each pattern as either shallow pattern if this is just matching some n-grams, or some semantic pattern if it is matching certain topic, right. Some topic is happening, it is called as semantic. So, then these students they actually annotate it and find if they are shallow patterns or semantic pattern. And now, these are some examples. So, like this is one key at layer 1, 449th key, layer 13th, 2989th key, and so on. Now, each key, what happens, you will see some top 25 prefixes, and you are seeing at least 3 of them should have some interesting pattern. So, now if you look at these prefixes, what it means is that I had taken this sentence and up to here I got the representation. So, xj at the lth layer, and I compare with this key. So, this will be at the first layer, xj first layer, and I will compare with the k1 449, right, and I find high similarity. Now, when I analyze this pattern, I find, right, they all end with substitutes. So, it is a shallow pattern, they end with substitutes. Similarly, here you find they end with basage and base, and it has some semantic, like they all talk about military. Similarly, this has some semantic meaning, a part of relation, one of the team, part of Indian delegation, among the top 10 in the list of films. Here again, it is a semantic relation, it ends in some time, right, between 3 p.m. and 7 p.m. Friday, from 11 a.m. and so on. And you have somewhere like TV shows semantic, like so this is about episode and daytime version, episode, so about TV episode. So, this was very, very exciting. I mean, so you just took top prefixes from the huge training data that match a particular key, only few prefixes, and you find some interesting patterns already there. And then they try to see, I mean, are these patterns consistent across layers? So, let us say we take like these are 16 layers, and then you are plotting what percentage of trigger examples in each layer are either shallow, semantic or not covered, right? They don't have a pattern. And what they found in the lower layers, like layer 1 to 9, you see the blue bar is much higher than other bars, right? That means the patterns are more shallower, right? So that means they often have prefixes that share the last word. But when you look at the last few layers, the upper layers 10 to 16, they have more semantic patterns. Right? They have prefixes from similar context, but without any clear surface from similarities. So this is what you identify from this. Okay. Now this was about keys. Now what happens with the values, right? Now remember what we said, the values will somehow associate with some distribution over data. I mean over the token, next token. Now how do you identify that whether this particular value stores some particular token distribution? So you see each value, what is each value in a layer L? This is just a d-dimension vector, and you have dm many values, right? So what can you do to find out what is the token distribution that this value associates with, right? Now if you recall from our discussion in this week itself, what I can do is that I can apply logit lens idea, or I can apply tune lens on this. This is a d-dimension vector. I apply this logit lens unembedding layer and I project it to the vocabulary space through an embedding matrix, right? And then I can find out what are the tokens, what are the probability for each token. So for every layer in memory dimension, what I will do, I'll compare the top ranked token according to VIL to the next token, right? So this will give me what is the token that has the highest probability. Now I can also look at the trigger example, right? So corresponding KIL for this, it had some top one trigger example. So what was the word that was following this, right? What was the word that was following this trigger example? Because ideally I should be following that word. So what happens? So they say, okay, according to KIL, what was the top one trigger? What was the next token to that? And you find out if the max token here, the highest probability token here is same as the token that followed the top one trigger example as per KIL, right? So just to again tell what will happen, like if you take this particular key and let's say this is the top one trigger. Now I will say what is the next word after this, and then I'll see if I'm projecting the vocabulary, the value to the vocabulary dimension and take the highest probability token, are they matching, right? That's the idea. If they are matching, then I have a very strong evidence that this stores the patterns and values store what is the next word following this. Okay. So then they plot this agreement rate. So that is, so top ranked token based on the value vector, projecting it to the vocabulary dimension, and the next token of the top ranked trigger example with the key vector, right? Now interestingly, they found that in the initial layers this agreement, right? So how often these two are the same is close to 0, right? So it does not give you much evidence in the initial layers, but as you keep on progressing, you see in higher and higher evidence. Like in layer 16th, you get roughly 4% evidence that the top token that you have in the projection from the value vector and the token that follows the top one trigger are exactly the same in 4% of the cases, and this is much more than chance. If you would try this on chance, so this would have 0.0004%, right? But now you are getting roughly 3.5%. So this is a huge evidence that they are key value memories. And they took some example values, like you take this particular value, 15th layer to 22nd value, and the top one prediction, the prediction for this is each by applying this unembedding matrix, and then they see among the top 50 trigger examples how often do they have each as the next word, and they find 68%, 34 out of 50 have each as the next word, right? And this is very interesting, and this is one example. So this will be your trigger, and this is what is the next token. This is the trigger and this is the next token, and this happens like 16% of times, here like 92% time, 84% time, right? And here even if it is just 4% of the time, This is a very rare term that you are able to capture, right. So yeah, this is another nice evidence that there is a feed forward layer. They may behave like a key value memory networks, right. So keys store the patterns and value the next token after that pattern. So now we are talking about another paper that talks about how do you locate and edit the factual association in GPT. Again, this is based on the key value memories. So let's say, so what is the idea? We will not talk about editing part, but at least identifying the factual associations. So let's say this is my prefix. The space needle is located in the city of, right. If I give this input to GPT, it will predict the true answer like Seattle. Now the question is, it will do that without even training, right. I mean, that means in its parameter this is storing this particular factual association. Now what is the mechanism by which GPT like models store this, right? That's the question that they were asking. So they tried to trace the information flow for answering this question, right. So what they will do, so let's say, so we will take the specific hidden states for the GPT model, and they will try to identify whichever have the strongest causal effect on the predictions of individual fact. Now, so what is a fact? They will say, okay, fact can be denoted as a tuple, subject, relation, object, contains subject, object and the relation. So let's say this is an example. Edmund Newport is the subject, plays the instrument, the relation, and piano is the object. So it's a subject, relation, object tuple. Now what they will do, they will give the subject in relation to GPT and let it predict the object, right. So S and R are given as input to GPT by natural language, and it predicts the object, like, so I am giving S and R as input, Edmund Newport performing on the, right, that is the subject and relation given, and you predict the object, piano. Miles Davis plays the, and trumpet is the prediction. So they do that, right. The question is, where do they really store this particular information? So they say, okay, we can go back to the transformer architecture, right, and what happens there. So because this is a causal network, this is autoregressive network, so information will flow only from left to right, right, and from the layer upward. So I can see the internal computation that happens in this entire computational graph as some sort of grid, right. We will see this, show this picture that they had pointed. So we have a grid of hidden states, right. So what will happen? So each layer will have hidden states, right, and I can see it as a grid of hidden states from left to right. And what happens? So at each layer you have the hidden state output, then you add the attention to that. So previous layer plus the attention output plus the feed forward output, right, the MLP output, and this gives you the next layer representation, and it goes from in a particular manner, right. So wherever you want to visualize it, right. So depending on the picture you want, you can see it top to bottom or left to right or up to down. So we will see this picture, right. So this is what happens. So you have initial hidden state, you add attention, you add memory. Now attention looks at just the previous layer, but all the words from the previous layer, right, the before this word, right, and MLP will look at just this word, right. This is looking at just this token. So this is looking at residual stream of only this token, while this is looking at residual stream of all the tokens that precedes including this token, right. So that's the difference across attention and memory network. Now let's look at the picture that they had. So that's why you can see from top to down, right, is the flow of attention. So top to down is attention, and left to right is the MLP, right, across layers. And this is your self attention. So you are feeding the word, the space needle. So this is broken into subword, is in downtown, and you predict the word Seattle, right. So this is your word that you fed, and these are your hidden states. So HI at layer 0, layer 1, layer 2, and so on up to layer L, right. So this will be HI for the word downtown, right, at layer L. So every word, every layer, you will have a hidden state, and you have a grid. You are passing the information from here to here, and in that you are adding attention, and attention, if you see this for this word, say downtown, will make use of all other previous words, right? So you get self-attention output, you apply MLP, you get this hidden state output. So you do that, and then you can predict the probability, right, after this computation. Now this is already a trained model. So they say, okay, you can compute the probability of given the subject relation, what is the probability of predicting the object. Now they did the causal mediation analysis. They say, okay, to calculate what is the contribution for each state towards this correct factual prediction, you observe all of each internal activation during 3 runs. So one is the clean run, right? So you just give the input, original input, you predict the facts. Then you do a corrupted run. So you damage the prediction, right, through corrupting this graph, this grid, and we will see how exactly they corrupt it. And then there is a corrupt with restoration run. There they will try to restore certain state and see what is the impact of that. Can it get back some of the damage, lost damage, right? Can it get back? So they had 3 runs: clean run, corrupted with restoration run. So clean run is simple, that is you provide the normal prompt, the station is a downtown, and you get the final prediction, no change, right? I mean, you get the probability, what's the probability of the correct prediction. Okay. Now what happens in the corrupted run? So they say, okay, what I will do, so we know, so subject is important. So I'll take the embeddings of the subject in the embedding layer itself, and I'll add some noise to that. So original embedding plus some noise, and noise should be such that it is sufficiently large in the standard deviation. So I add some noise so that they are really corrupted. And what will happen if I corrupt this? You see, even to compute, see the embedding are fine, but even to compute any hidden state, right, even to compute this, I need this previous hidden state. So even this will be corrupted. So everything that I see in this grid will be corrupted because of this, right, and my output will be corrupted. So they compute what is the probability of Seattle now after I have corrupted the subject, right. So I have the clean run, I have the corrupted run. Third, they have the corrupted with restoration run. So where they say, okay, now I have corrupted this run, but what I will do, I will restore some of the hidden state. That means, so corruption is already there, but at this point, rather than computing it via this network, via the connection, we will directly use the clean runs hidden state and substitute here, so that I have some restoration impact on that hidden state. Now again, I mean, nothing else will be changed. So others are anyway corrupted, but at least I have put back one restored state, right. So they will try to restore some states and see, I mean, so you have an original probability, you have probability after corrupted. After restoration, do you get back somewhere close to the original probability, right. So this is the thing. So you have this clean run, this is the corrupted run, and then is the restoration that you are doing, where you are substituting a clean state here. You see, I mean, everything else is corrupted, but this is clean. And now after you substitute, you will compute, you will next propagate this information later on, right. So it will have some effect of the original state, right. So it will possibly, this probability will be slightly better than the corrupted run. And now this can give you an idea like what is the hidden state that you have to restore so that you get a highest jump from corrupted, right. So which hidden state is the most important, and that's what they identify as the average indirect impact. That is the, what is the probability after you restore one of the state minus the probability of corrupted. So when you corrupted the embeddings and then you ran, what is the probability of the output and what is the probability of output in the restoration. And what they find, so they tried with 1000 prompts, and they tried it at multiple places, like first subject token, do I restore that position, middle state subject token, last subject token, first subsequent token, further tokens, last token. So you can restore any of these, right. So it's up to you which hidden state you want to restore here. So it can be subject state or later on last token. And at what layer do you restore? Like you have you can restore at just the initial layer, or you can restore at middle layer, later layer. And then they tried all possible combinations, right, all possible grid, and see how much do you gain, what is P restore O minus the corrupted probability. And you see, I mean, wherever you will see some blue things, that's the where you get a gain. Interestingly, they find two interesting sites where they have gains. Now, last site is something that is not so surprising, because what are you doing? You are replacing back the hidden state. Now, if I do it at the last layer, right, so I can directly predict the word, I mean, as if nothing has happened. If I have this at the last token, last site, I can easily take a prediction. So this would be perfect 100%, right? I mean, I will have a complete behavior of the clean state. So this is not very surprising that if you do it. But what is surprising is that even in an early site, right, and not initial layers, if you do the last subject token restoration, that also has a lot of positive impact. Right? So they call it early site and late site. And then they further try to analyze, I mean, so good. Now, what if I restore not the hidden state, but restore the MLP, right? They saw that they cannot just restore one MLP, they have to restore, I mean, some MLPs across layers. So not this direction. So they will restore some MLPs across layers. So say we can restore MLP for 10 layers continuously and take the centroid, right? I mean, center point, center of interval for 10 patched MLP layers, and see what happens. Now they find again that I mean, there is only one site, that is the early site. So mid-layer MLP has some interesting role in preserving this information, that if you restore the MLPs, this is able to get back the probabilities. They tried the same with the attention layers. So that they found that okay, it happens only in the late site. It does not have some effect on the early site. Now this may have some connection in what we were saying in the previous lecture, that this MLPs try to store this knowledge facts, the mid-layer MLPs, right? And that is what is the early site. So if you restore them, that has some nice effect, but that is not shown in the attention layers. Now they also did some causal tracing. Okay, what if after I restore in hidden state, I see where the connection of the MLP from that path, what happens then, right? So idea is that if MLPs are important, I mean, so what will happen if MLPs are important, after severing it, I will have a huge dip in the performance, right? And that's what they saw. Similarly, they also sever the attention layers in that path. So because you see there are two paths, one is going via the hidden layers, another is going via the attention. So they're saying which path has the more impact. So they try to sever connection from just the MLP, and similarly they try to sever the connection just with the attention layers, right? So you modify the computation graph by severing the connection of MLPs, and you compare the average net effect with and without severing the MLP, right? And that is what tells them what is the impact of this mid-layer MLP modules. So this is the picture. You see, you have layer 1 to 10, up to 20, 20 to 40, and this is a single state restoration indirect effect. How much probability do you increase, right? And this is what you see. Mid-layer is very high. I mean, it's reasonable. Now, if you sever the attention networks, it goes down, but not so much, right? So attention have some role, but not so much. But if you sever the MLP connection, that goes down drastically, right? So MLPs have huge role to play here, right? So that's what they bring out, that MLPs have huge role to play. And this is again coming out from the mid-layer MLP modules, that, and you see later on it does not have so much of difference. So mid-layer MLP is what they say is what is storing the knowledge facts. And later in this paper that we will not discuss in this lecture, they also try to use this fact to edit the model, do model editing. So if we know this is where the information is stored, I can use that to edit the information. Okay. So yeah, various papers that we cited in the slide are the references for this part. Thank you, and we will then come back with the fourth lecture. We will come back to the ethical considerations. Thank you.